Good day everyone, my name is Eduard Zubchuk. In the next few minutes I'll present to you our paper titled Efficiency of Short Text Classifiers for Payment Classification. The presentation will go as follows. First, I'll introduce the short text specific and related processing problems. Then I'll review the relevance of this topic in current natural language processing or NLP research and previous work related to this topic. After that, we'll talk about the data we used in this research work and the different approaches that have been used in this study. The last section of this presentation will be about improving results using model fine-tuning and conclusion of this work. So let's start with the short text specific. In this study we work with the remittance notes. That is short texts that are part of a payment documents. Short texts have distinctive peculiarities and problems associated with them. The first one is sparse. Short text contains from 2 to a few dozen words, so it does not provide enough information and general context for traditional text classification approaches. The second one is unbalanced distribution. Class instances are limited and the distribution of the instances across all classes is unbalanced. The third one is non-standard. It's quite short text contains a lot of spelling mistakes and noise. And the last one is the big data bottleneck, which means that it's not possible to manually mark up all instances of a large data set. So a limited number of marked up instances can only provide limited information. All these features make traditional NLP algorithms such as latent semantic analysis not quite as effective as they can be with the longer text when we are dealing with the short text classification. So there are several classical approaches related to the short text classification. We will review 4 unique methods that have been used for this topic since early 2000s. The first one is latent semantic analysis, or LSA. The core idea of this approach is using vector space models for transformation word into vector representation in some vector space. The dimension of vector space usually is set by researchers, taking into account features of the text they handle with. This approach works really well with long text, but however, it cannot handle the main features of the short texts. The second method is, or the group of methods, is ensemble methods such as boosting and bagging, whose main idea is to combine several weak models' predictions to improve the final accuracy. It had widespread in 90s and 2000s, while modern ensemble approaches can achieve high accuracy even on such complicated data as we used in this paper. Decision tree and forest classifiers. This approach uses a hierarchical decomposition of the data space, and as the name suggests, these hierarchical decompositions look like the default tree structure or the forest structure. These methods are quite effective in the short text classification task, but can be easily overfitted, and they are very sensitive to the data noise. The last approach is neural networks. Neural networks approaches usually reach the best performance and accuracy handling short text classification task. In this research we used fast text and BERT models. The last one can reach state of the art in case it was used in a correct way. In this work we operated with a data set of about 630,000 of remittance nodes. All nodes were divided by regular expressions into 5 classes: assembly work, building materials, food, tobacco, and other. After removing duplicates from the dataset, about 83,000 instances have left. Non-letter characters and stop words have been removed from the transaction descriptions. It is important to understand that regular expressions markup contains error and cannot be gold standard itself. At the same time, as the results of our work show, the trained models show a high level of consistency with the regular expressions markup and partially correct markup errors. The data was balanced, a part of the others class was removed, and split into training and test subset in 4:1 ratio. As I said before, in this study we used BERT and fast-text models. Also, we compared it both to the TF-IDF combined with naive Bayes approach. Let's take a closer look at each of them. TF-IDF plus naive Bayes. Ter frequency inverse document frequency is one of the most simple text vectorization methods with subsequent naive Bayes classification. It is based on detecting and counting specific keywords for each class. The advantage of this method is simplicity and its swiftness. However, TF-IDF does not consider variation in word forms, which is extremely important in the Russian language, with its endings, word forms, etc. It can be solved by stemming the source text, which means trim the ending and making general word form. However, the nuance of subject area is a large number of typos, abbreviations, and strong class imbalance, which complicates the classification and makes it almost impossible for poorly represented classes in the dataset. FastText is the open source Python library. It usually shows good results at remittance nodes classification or short text classification. This method is based on the approach of text vectorization with the subsequent assessment of frequency and significance of words belonging to a particular class. In simple terms, the idea of the fast-text classifier is quite similar to vector space models. BERT, or bidirectional encoder representation from transformers, is a neural network that is often used for natural language processing, or NLP. With a large and well-marked dataset, this architecture has the greatest potential among all algorithms described in our paper. We use diversified pre-trained Rubert network from the Pavlov with preprocessing text, with the stop word deletions, stemming, etc. To compare these models, we used the weighted average F1 score metrics. Now you can see the model accuracy metrics on the slide. It should be noted that these metrics were used with a dataset that had been marked with irregular expressions. The result of this work primarily relate to the approximation properties of classifiers. From these results, we can conclude that the accuracy of FastText and BERT is quite close, while the BERT model is about 1,000 times slower. Based on this data, we recommend the FastText model for further usage. As I said before, a few sections ago, weak representation of some words in Russian language reduced the performance of the FastText model. To solve this problem, we created 5 synthetic examples of these words in Russian and added it to the training dataset. After fine-tuning, the model successfully started to classify short texts with these words in the correct way. However, the side effect of this method was the classification of the single root words to the same class, which is not quite accurate. By this experiment, we showed that the model can be fine-tuned for getting more accurate results for any words in Russian language, but also can be overfitted. Accounting for the combination of perceived performance and accuracy, the FastText models was recommended as the replacement of the regular expressions. It should be noted that models we described are statistical and are not able to have 100% prediction reliability. The accuracy during the commercial use may be lower due to word construction not represented in the training dataset. We can improve the quality of the models by enhancing the training dataset by adding synthetic data based on vocabularies for each category except other in a future learning pattern. In addition, different words in the dataset have different weights. The other way to improve model performance is the usage of iterative pseudo-labeling for additional training due to its effectiveness in condition of limited labeled data and high data noise level. Thank you for your attention.